Yes, in this chapter, we are going to cover the basics, the fundamentals of additive manufacturing. And to the end of it, we'll try to compare some main properties of additive manufacturing with CNC or with other conventional manufacturing operations. Let's start with an video, an interesting video. This is, as you see, the title is called as 4D printing. This time it's not 3D. We have four dimensions. What is the fourth dimension? Any guess about the fourth dimension? What it might be? We have X, Y, Z. What is the fourth dimension?
Maybe the table is spinning, rotating.
No, not about the position, not about the orientation of the table. Yes, there's an answer here on the chat area. It's time. Yes, you will now see that after printing, it changes. Oh, we have a strange music. Yes, turn it off or maybe decrease the volume. If they are using a special material and using an injector kind of thing, as you see here, they have special patterns. Right now it's 2D almost. And once they have another layer, it will be 3D. Yes, now they are extruding the second layer, so we can say that right now it is 3D. But now we will, in a moment, see that they will put it in a special solution and it will move actually. Yeah, they are putting it just simply into water. As you see, it changes its shape in time. So that's why we call it a fourth dimension. And these days we have some research on 4D printing, especially on different types of material shapes. And they are trying to produce some specific parts which change their shape in time, or changing their shape with some specific simulation by temperature, let's say, or by humidity, by pressure. Once the pressure is high, then they change their shape, or once the current flowing through the part is a bit different, then they change shape. So we can call all these cases as 4D printing. So let's go back to the fundamentals of this course. The name of the course is 3D printing and additive manufacturing. So what do you think? What is the difference, or do we have a difference between these two terms? Why I prefer to use 3D printing and additive manufacturing as the name of this course? Anyone want to answer? Can they simply unmute themselves and tell us the difference between 3D printing and additive manufacturing? Whether, or if there is no difference, you may say that they are almost the same. No questions, guys? No answers, actually, I'm sorry. So, yes, there is an answer. 3D printing is a version of additive manufacturing. Somehow we can say that, yes, these days additive manufacturing is much more common. And I can say that in the earlier days, people actually love to use 3D printing since it was a novel technology. And in order to describe its fundamentals easily, they want to use this term since we have 2D printing for about a century maybe, and now we switch to 3D, which means that we are producing, we are printing, we are extruding some parts in 3D. In the earlier days, they love to use 3D printing, but now since we have various types of 3D printing, and we prefer to use additive manufacturing. And according to the standards, we have an standards ISO and ASTM. They prefer to use additive manufacturing term. As some of you pointed out, it's a much broad term. It covers all the topics related to such printing processes, three-dimensional printing processes, but still, for the desktop versions, the desktop type of additive manufacturing, we prefer to use 3D printers, as you know, the simply fused deposition modeling or fused film fabrication ones or SLA printers. People still love to use 3D printing, and it's quite easier for children to understand the fundamentals. Once you say 3D printing, they easily understand what is going on. So what about another term, democratization of manufacturing, and how can we relate it to 3D printing and additive manufacturing? Any idea, anyone interested can unmute themselves and tell us about this term. Why do we use democratization of manufacturing? What do you understand from the democratization of manufacturing? What happens if the manufacturing is democratized? This is obviously not a political science course, but we can briefly discuss democratization. Yes. Yes, here one answer, everyone can manufacture, yes. And once you do the democratization in manufacturing, that means every people actually will have access to manufacturing. Without 3D printing, if you don't consider the desktop printers you have at your home offices, it's quite impossible to manufacture something easily. What you need to do is to go to some job shops, go to some factories, and try to manufacture a specific product. But once you democratize it, and that means you can easily on your own do the manufacturing. And this is actually become possible with the help of such 3D printings. And that's why we say that with the help of additive manufacturing and 3D printing technologies, the manufacturing is democratized now and everyone has an access to manufacturing facilities. Yes, the access is the most important one, and also everyone can easily manufacture. These are the fundamental things while we consider the democratization of manufacturing. And that's why we have a maker movement these days. Without 3D printers, we wouldn't have a maker movement. So what is actually how this additive manufacturing is developed? In the earlier days, once people invented some 3D printing equipment or additive manufacturing equipment, they called their machines as rapid prototyping machines, since their fundamental goal was to manufacture some examples of their final products. Not the final product, but their just prototypes were being manufactured in the earlier days. But with the help of maker movements, now we make use of these actually printers as the final product manufacturers. Since if you consider, let's say, this toy, this rabbit, this is a printed one, and I don't say that this is a prototype, it's a final product, it's a toy, or you may have such a metal part. This is also 3D printed, a metal one. You can see the emblem of our university, and right now we are using additive manufacturing for also manufacturing, direct manufacturing. We will discuss all these terms, and these days the printers, additive manufacturing machinery is not only used for prototyping purposes, they are also used for obtaining the final products. So how actually does additive manufacturing things work? Not that complicated. What you need to do is to simply design a part in any CAD software. Here you see an cup. You see teacup. It's designed in CAD software. It has different features. Then what we do, we need to use a computer manufacturing software. This will be the software of your printer, of your additive manufacturing machinery. We'll discuss the details later in the upcoming chapter, but I can say that you should first design and then import it into that manufacturing software, do some modifications in that manufacturing software according to the requirements of your part, according to quality you want to have at the end of the manufacturing. Since if you compare these two pictures, the main difference is that you see some layers, right? Since additive manufacturing depends on layers, what we do, we slice each part and then print one layer and then the other one. So that's how we build the parts. And the most important parameter is the layer thickness in additive manufacturing. It determines the quality of your overall product. Here you see we have a staircase-like shapes around the outer part of the product. But depending on the capabilities of your printer, you can decrease the size of these, the thickness of these layers. You see? And this one is printed by using an SLA printer. I think you cannot easily see the layers. But maybe in this FDM one, if you can see it, I'm not sure, but you may see the layers. This is printed in that direction. This is Z direction, X, Y, and you can see the layers. Yes, there are some questions, but we will discuss the details of these slicers. These are the CAM software. Yes, Cura is an slicer and it's free. You can easily download and play with it. We will be discussing Cura and other similar programs in probably next week or in the third week. So in summary, I can say that you design it in CAD software and import it into complete manufacturing software, like your friends pointed out there. Cura is one of them, and each printer company have their own software, but Cura is the most popular one for the deposition modeling. And in that software, you do some settings, play with infill parameters, layer thickness, and then try to increase the quality of your overall product. And finally, submit these generated commands, the trajectory of your head of the printer in some different formats to your printer, to your additive manufacturing machinery, and then start the fabrication. And this is also the same. These main steps are the same for SLA technology. It doesn't matter whether it's FDM or SLA, or even for the metal ones, they have a similar pipeline. And this is what I call is design and fabrication pipeline. Since we have many steps, it's a kind of pipeline. You start the design, you do some modifications in the CAM software, you generate the commands. Usually we use G-code commands, G and M commands, and then generate a file, a machine file, and submit it to the machine. So overall, this is called as design and fabrication pipeline. Questions, guys, up to now about these fundamentals? So where can we use actually these additive manufactured parts? Why do we use rapid prototyping or 3D printing or additive manufacturing? We have three main reasons. First of all, sometimes we need to check whether our design is okay. We look at the form of the design. If you assume that this is a mechanical part, or this one maybe, you try to use additive manufacturing to see whether the form of this part is fine or not. That's one of the reasons why we use additive manufacturing. Another one, you may use it for fitting, and this might be a part in your assembly, and you may check whether it's fitting into your, let's say, assembly or not. So for fitting purposes, we use additive manufacturing, or maybe lastly, you can use it for checking the function. For instance, let me try to show it like this one. Here you see we have a kind of a script here. You can check your design whether it's functioning properly or not. If it has some moving parts, so then that means you are printing the parts to see whether your assembly is functioning properly or not. And we also have many other reasons, but these are the main ones, the three major reasons why we are using additive manufacturing. So here's a detailed version of the pipeline, the design and the fabrication pipeline, or our textbook actually names as the generic additive manufacturing process, but they are the same. So let me go through it quickly, and you'll have some discussions about the details. So what we do the design in a CAD software. We convert it into a special file format. We will discuss this file format in a moment. After you have this file format, it's the same, but it's a triangulated version of your initial design. And then you transfer it to the CAM software, computer-aided manufacturing software. Our textbook names it as the machine, but it's actually the software, the CAM software of your 3D printing system. And then you do some setup. This setup actually is done on the CAM software. You adjust the parameters of the printing process. You may use some available parameters, but if you want to maybe modify the layer thickness or other issues, you should do it in the fourth step of this pipeline. And then what you do, you simply transfer these comments into the machine with different means depending on the technology, depending on the type of actually model you are using. These steps might be a bit different, but the main idea is the same. You generate some codes or some machine files and then transfer them to the machine. You can do transfer by Wi-Fi connection, by USB, by SD card, it doesn't matter. You need to simply transfer these commands to the machine. You do the fabrication, and then you simply remove it. Sometimes, depending again on the type of technology you are using, the parts might be in a bed of powders. This time you need to do some post-processing. You see here the seventh one. For instance, if you, I don't know, you can see or not, here you see there are some support structures. We will discuss the details of them. But in the post-process part, regarding this example, you need to remove the support structures. Or if it's an SLA one, again, you can have support structures, but they're a bit different than the support structures of the FDM. But the fundamentals, the main idea is the same. While doing the printing process, some parts of the parts may not be supported. If they're in air, then they will probably fall, or there will be deflection, and the quality, the overall quality of your part will be very low. So that's why we need to use, for some specific parts, the support structures. And lastly, this is the application part. If it's a teacup, then you can simply use it. But most important issue here is that it is made of plastic. It's not biodegradable. I don't suggest you directly use it, but this might be maybe a ceramic part, since we also have some ceramic printers, or they may have done a coating application in the seventh step. In this post-process, you will see that there are also some coating possibilities. You can do that, and later you can directly use this part, the design part, in your application. So let's go into details. This bunny, by the way, is called as Stanford bunny, and in our research, we mostly use such models in computer graphics and 3D printing community. we love to use this bunny. It's called as Stanford bunny, and you can easily download the STL model of this file, this model on a website of Stanford University. And the original one is, as you see, 13 MB. And what we do design the part, and then you need to convert it into an STL file. We will discuss some details, but this is actually one of the main steps in the generic additive manufacturing process. For instance, you do design in NX or you do design in SolidWorks, it doesn't matter. You can do it Rhino, but most of the additive manufacturing software only accepts such specific file formats, STL, OBJ, or different ones, but they only have information about the outer surface. And how do they represent the outer surface? By simply using triangles. As you see, this is a triangulation of the outer surface, and we have, here you see, more than 200,000 of triangles, and these triangles are representing the outer surface of the bunny. And then what we do the slicing, since additive manufacturing is a layer-based, mostly about 99% of the time is a layer-based manufacturing methods. We need to divide this initial model into layers. We can sometimes call it as slices, it doesn't matter. Depending on your initial settings, in this example, as you see, we have 838 layers, and you can see the layers, but this is a bit different view, but they should be all horizontal. The layers are all horizontal for the 3-axis printers, but if it's a multi-axis, then you may have different slicing planes, but for the conventional desktop printers, the slices are always horizontal. So once the slicing is performed, then your CAM software, computer manufacturing software, should actually generate commands. And as you see, for the fabrication of this bunny, we need to have this much comment, more than 600,000 comments, and they correspond to about 20 MB of a machine file, a G-code file. And then we simply send it to the printer and try to fabricate our parts. This is an example of a G-code file, not that complicated. For the FDM case, actually, this is an example of an FDM. Here you see, we mostly use G1 command. If you remember from your 202 course, it's for G1 is used for machining. And here we use G1 for extruding material in the FDM process, but as I said, for different additive manufacturing processes, they may not use G-codes. They may use their specific commands, specific file formats, but for the FDM ones, they for about 99% of the time, they use such G-codes, and G1 is responsible for extrusion of the material. And again, we have G0 commands. G is also the same for CNC machining. With G0, you have fast motions from, let's say, one point to the other point without extruding any material. And after writing the initial commands, the rest is not that complicated. You define the final destination in terms of global coordinates, X and Y coordinates, and then you need to define the amount of material should be extruded while going from this previous statement to the next one. So the difference between those let's say E-axis is defining the material. So if you take the difference of these two, it will give you the amount of material which should be extruded while going from this point to the next point. So as you see, it's not that complicated. There's a question about printing time. I think I printed this one. I don't remember exactly, but since the height is not that much, maybe 3 hours or 4 hours. I should check it exactly. Yes, we will discuss the details of STL in a moment. There's a question about STL. I will now discuss it on this slide. So this is another illustration of the generic additive manufacturing process. I said many times that we start with an CAD design and then convert it into an STL file. So what do we have in the STL file? We simply have triangles. Here, our example is a very simple one. Let me use my pen. Yes. Oh, this is closed, so let me open it. Yes. So in the next step, we simply do a triangulation. So this is a very simple one. I will divide these square surfaces into triangles. And you see in the second step, we represent this actually cube by using how many triangles? We have 6 surfaces. 2 is fine actually for a single square space. So we have just 12 triangles in this conversion. And by using 12 triangles, you can represent a simple cube or any kind of box shape. It doesn't matter whether it's a cube or a box. Still, you can represent it by using 12 triangles. But if it's an organic shape like bunny, you have seen in the previous slide that there may be about hundreds of thousands of triangles, and this will increase obviously the size of the file. So why do we actually do this conversion? There are several reasons. The first one is that we have many CAD software, right? Right here, we have SolidWorks, let's say, we have NX, we have Rhino. I'm using a tablet, that's why my writing is not that good. In real life, I'm not writing that bad. This is CATIA, let's say. We have hundreds of CAD software, right? But let's assume that you have a single printer, and assume you have an Ultimaker to go printer, okay? This is your 3D printer. So if that's the case, and if you're a single printer and the people actually who are using your printer might have different, let's say, CAD software. They may have installed SolidWorks, NX, or different CAD software. And if you directly use the output of the, let's say, SolidWorks, output of NX, Rhino, and let's say, oops, what happened? Let me quickly go to here, yes. Then things will be highly complicated. You will not be able to write, let's say, specific software. It's your, I'm sorry guys, I press the button there. Yes, let me move it like this one. So in summary, I can say that you have a single printer, you have multiple CAD software, and if you want to communicate with that printer, you need to write specific scripts for each CAD software, which is impossible since there are hundreds of them. If you are a, let's say, printer manufacturer, you cannot do that. You need to invest thousands of, let's say, bucks, millions of bucks into writing specific scripts for each CAD software. But that's why people prefer to convert the designs in different CAD software into a common format. And this is the main reason why we prefer to use a common format. Although it has problems, people prefer to use the STL formats. The reason is that since in the earlier 3D printers, the main actually concern was to print the outer shape. The interior was nothing that important, since if you remember the functions of the main functions of the additive manufacturing, we use it for form checking, fit checking, and function checking. So if these are the goals, then you don't need to focus on the interior of the parts. The outer shape, the overall part, is the most important issue, and that's why people just focused on the representation of the outer surface. They didn't consider whether the interior of this shape is filled completely or is half filled, quarterly filled. It doesn't matter. Their main concern was the outer shape, and that's why they focused on a file format, which is only responsible for representing the outer surface. And they come up with a simple solution, such an STL file, and you see that not that complicated. What do? You simply divide the surface into triangles, and any surface can easily be represented with triangles. So that's why they come up with such a simple solution. And I think this is the answer to one of the questions there. The interior is not important for us. The outer surface, the shape of the product, is the most important issue. Yes, Berkay, they want to define the outer surface. And you are right, one of your friends pointed out that they do these actually triangles affect the quality. Yes, for this cube shape or for box shapes, when you do the conversion, you don't lose any information. If you look at the overall shape, since we have sharp corners, sharp edges, we don't lose any information from the geometry. This geometry is exactly represented once you do the conversion. But think about such a cylindrical part, okay? If you do the conversion, if you do the STL conversion, then you will lose some information about parameters, since you cannot represent this circle with just triangles completely. You will lose some dimensional accuracy. And that's why for such organic shapes, also for curved surfaces, it's better you increase the number of triangles, you increase the resolution of your STL file, and then continue with the rest of the steps. Otherwise, as your friend pointed out, you will lose information about geometric dimensions, and your overall product, the dimensional accuracy of your overall product, will be low compared to the original design. So I will have a break after I finish this slide, okay? We do the conversion, and then we transfer this STL file into the CAM software, computer manufacturing software. We adjust some parameters and then do the slicing. Once slicing is performed, we generate a machine file, and this machine file may be composed of just G codes, M codes. As you see here, you have M codes and G code. This one is responsible for the fan speed in the extrusion process. And another issue I didn't mention here, but while we are discussing the FDM process, I will go through the interior, what we do with the interior. I didn't show it here, but in the CAM software, there are lots of parameters about interior. You may have different infill patterns, diagonal ones, different circular ones. It's up to you. There are hundreds of types actually. You can select the best one for your case, and the CAM software will generate the trajectories for you. After you have it, you simply transfer it to the printer and do the fabrication. And if it's an FDM, you will have such beads of filaments, beads of material, such lines will be extruded. And if you look at the bottom of this bunny, I think you can see the lines clearly. But for the it's quite difficult to see it since here we use a different material and we use a laser source. It's quite difficult to see the path, but it's somehow similar to the FDM technology. It again generates some paths for the laser head. So now let's have a break, and then as you now I think know the fundamental, this is the main design and fabrication pipeline. And this is almost the same for all additive manufacturing technologies. Design, convert it into STL files, send it to the CAM software, do some modifications, do parameter setting, generate the machine file, transfer it to the machine, and fabricate it. What are the other terms we use for additive manufacturing? In the literature, there are many terms, but as I mentioned, these days we prefer to use simply additive manufacturing, or in short AM for additive manufacturing or 3D printing. But in the earlier days, you were using rapid prototyping or stereolithography, since the first developed additive manufacturing methods is stereolithography. That's why people were using stereolithography as the name for all 3D printing processes. And sometimes you may see the term layer-based manufacturing, since for most of the time we are taking layers and printing materials, extruding materials on top of each other, layer by layer. That's why some people love to use layer-based manufacturing. And in Turkish, in the earlier days, some people were using katmanlı imalat, which means layer-based manufacturing, but these days we prefer to use eklemeli imalat or eklemeli üretim, but imalat is much better. Once you use üretim, actually industrial engineers love to use production or üretim. That's why as mechanical engineers we prefer to use eklemeli imalat in Turkish. And another terms we can use as a freeform fabrication or solid freeform fabrication, since you don't have any limitation in terms of the surface forms of the parts. It doesn't matter whether you have a complicated one or a simple one, your additive manufacturing machinery will be able to fabricate that part. That's why people also love to use the term freeform fabrication or solid freeform fabrication. And this is the first one is the least commonly used term, automated fabrication. Since it's a very broad term, you can use it for any manufacturing method. Any manufacturing system can be automated, so I would prefer to use that term. So what are the benefits of AM? Why do we need to use additive manufacturing, and what are the possibilities in near future in these times? First of all, it's now one of the fundamentals, one of the pillars of the fourth industrial revolution, Industry 4.0. It's one of the main topics in that revolution. So the motto is, what you see is what you build. So you don't have any limitation. You can design anything without considering the limitations of your, let's say, conventional limitations, and then you can easily build that design. We have some concerns. We have some actually rules regarding support minimization or quality improvement, but the limitations are not as much as the limitations we have in the CNC machining or conventional manufacturing operations. Another important issue, another important advantage of additive manufacturing is that we have less steps, which actually we can easily automate these steps. What do we do? Design should be done in any manufacturing process, whether it's CNC or injection molding. So it's a must for all manufacturing processes. But if you consider, let's say, an injection molding process, after designing your part, you need to design the molds and do some analysis whether the design mold is okay or not, whether you will be able to produce the design part actually, or you need to design some post-processing steps, so it's highly complicated. Or if you consider the CNC manufacturing, CNC milling, let's say. What do you do again? You design the part and then you import it into CAM software, let's say Siemens NX CAM software. And in that platform, you need to decide on the processes. You need to first do maybe face milling, and then maybe some end milling operations, some drilling operations. So you need to spend lots of time in that CAM software. But if you compare it with additive manufacturing, and in Cura just a moment ago, I simply imported the design, and then if the default settings are fine for you, then you can simply send it to the printer. So that's why actually we prefer to use sometimes the term 3D printer. Since it's not that complicated, everyone can use that machine. You download the design from your web browser, import into that CAM software, Cura, and then just click a button. It's very similar to printing papers, printing your documents. You open it, and then just click print button and it prints. That's why actually we are using the 3D printer term for the desktop ones. This is somehow similar. We use less number of processes, less number of sub-processes, less resources. Can anyone tell me about reduced resources? So why it is advantageous, or how we are using less resources?
For traditional manufacturing, we produce chips. It's called talaşlı imalat, even in Turkish. For this, we can reduce the number of non-used material. We can reduce waste. We can even optimize support structures for this.
Yes, correct. Thank you, ODTÜ. We have, most of the time, we don't have waste generation, or sometimes we have little waste due to these support structures, and as your friend points out, we may try to optimize design, change the orientation so that there will not be a requirement for the support structure. So this is one of the advantages why we use less resources. Another thing is that since in a shorter time we can do it, so we are using less time. Since time is again a kind of a resource, and we are using less software, less power in terms of we are using mostly smaller machines. But if you consider metals, somehow the energy requirements are almost the same. But regarding the materials, due to not removing, not actually subtracting the material from the initial workpiece, we don't waste extra material. So that's why we can call these additive manufacturing systems as sustainable manufacturing operations. And this is another highly important advantage of additive manufacturing. We are using a sustainable operations. Any questions, guys, about the benefits, advantages of additive manufacturing? Yes, we have another good answers on the chat. I just seen them now. Thank you for the answers. Any questions regarding the advantages of the AM methods up to now? Okay. So there's a question about mass production. So your friend is asking whether these methods are fine for mass production or not. What do you think? Can anyone answer this question? So can I produce, let's say, thousands of this bunny easily, or should I print them one by one?
Hocam, if you don't have any time constraints, it's quite possible. Ama 3D printing is not as fast as, like, let's say, injection molding.
Sure, yes. Injection molding, especially for such plastic parts, if you have a mass production case, it's better you use injection molding, but if it's, let's say, around 50 number of this product or hundreds of them, you may, if you have a large printing area, you may build maybe tens of this part at the same time. So we can say that it's not always suitable for mass production, but for let's say medium production or low quantity production, AM is a better solution. Since if you are not going to produce more than hundreds of them, then the injection molding or other methods might be costly. It's better to use additive manufacturing instead of that injection molding processes. So as your friend pointed out in the chat area, the number of products you're going to fabricate is the main concern. If it's some between medium numbers, then AM is fine, but if it's a very high number, then you should switch to some different methods depending on your type of material you are using, depending on your application. I think this was a good question.